So, in previous class I have started the topics, that is physics of welding. There I have already discussed about the welding arc and how the welding arc initiated and how the welding arc sustained in between a gap, that I have already discussed in details. And I have started little bit in welding arc structure related thing also. Today I will first discuss in details about arc structure, then I will go for potential drop characteristics of arc, then how to what is arc power. In details I will discuss about arc power. There we will see how to find out the optimum arc length, how to find out the optimum arc power, and at the end of this lecture I will discuss arc initiation. So, first of all, last class I have already discussed in arc structure. There we have observed that due to the ionization and emission process, in between the arc there developed a arc structure. This arc structure, due to this emission and ionization of arc gap, there generate different zones. Zone in the sense, that is why this arc structure can be categorized, arc structure zone can be divided into 5 different zones. So, here what we observed last class, we have observed that this is a electrode, this is a electrode, and this is the workpiece. So, generally electrode is cathode, generally here let us electrode is cathode terminal, cathode, and workpiece is, this is job or workpiece, which is generally positive terminal. So, this is generally called anode. So, what we observed last class, we have discussed that this is a arc. So, then this arc, what we observed last class, a arc is generated, a arc is generally generated between this gap, between this gap. So, this is generally arc. So, what we observe, so here what happens, here generally inside this arc, due to ionization and emission, electron come out from this cathode surface, and this electron, so what we observe here, electron is negative charge and there is positive charge, ion is a positive charge. So, what happens in a arc structure, this positive charge is attracted by this cathode terminals and this negative charge is attracted by the negative terminal. So, generally due to this flow of this electron and ion and its concentration over the anode surface and cathode surface, this arc structure can be divided into 5 different zones. What is this 5 different zone? So, first zone is called cathode spot zone. What is this 5 different zone? One is called cathode spot zone. One is called cathode spot zone. This is relatively a very small area on the cathode surface. So, this cathode spot zone is a very small area of this cathode surface, which I am generally that this is in a very small area. This is called cathode spot zone. So, this is actually a relatively very small area on the cathode surface, which generally help for emitting the electron. So, from here generally electron is emitted. So, from here generally electron is, so emission is taken place from cathode spot zone. Now, what happens, the second zone is called cathode space zone. What is cathode space zone? That also we should know. Cathode space zone means what happens, as this cathode is negative zone, that is why this cathode is generally attracted this positive ion. A positive layer concentrate over a space within this cathode surface is there. So, a small zone we get where concentration of this positive ion is there. So, this is actually this cathode space is a gaseous region, which is adjacent to this cathode spot zone. And what happens, its thickness generally within a range of this cathode space thickness generally within a range of 10 to the 5 power minus 2 millimeter, or we can say 0.01 millimeter. Within this range generally a small gaseous zone is created, where generally a positive layer of ion concentrate in front of this cathode spot zone. So, it is a gaseous space actually. This region generally have positive space charge. So, voltage drop here will be necessary, because cathode spot emit electron. So, what is the electron coming out from this cathode spot, that electron generally have to penetrate this cathode space, because this electron is attracted by this anode surface, which is generally positive, because as electron is negative, that is why what happens, this is generally attracted by job or anode, which is generally positive charge or positive terminal. So, this positive terminal attracted this emitted electron towards the job. So, what happens, as this cathode surface is covered by a cathode space region, which is generally positive charge, here so the voltage drop is necessary, as the electron are to pulled from this region. So, here what happens, whatever the electron is emitted from this cathode spot region, that have to pulled from this cathode space region and flow towards this anode surface. So, as the electron is getting some resistance over this region, so what happens here, generally develops a sharp drop of voltage, here generally develops some voltage. So, here we get a sharp drop of voltage region. So, this is generally called cathode space region. The third zone is called arc column. It is the visible portion actually, arc column. It is the visible portion of the arc structure. Here generally we get the arc plasma. Arc plasma is generally the ionized gas. So, whatever the visible portion we are getting, that is generally called, this is the arc column. So, here what happens, ionization is occur. In this zone generally ionization is occur. So, in this zone the voltage drop is not that much of sharp like cathode space zone. Here generally voltage drop is not sharp in nature. So, here marginal voltage drop also is occur. So, due to this arc length. Now, fourth zone is called anode space zone. Anode space zone. Anode space means here a gaseous, this is also a gaseous zone, where negative charge is generally concentrated in on the top of this anode surface, this negative charge. It is also a gaseous space. This anode space is a gaseous space, where generally concentration of negative charge, that is electron, is generally concentrated over this surface zone. Now, here also a sharp drop of voltage is occur, because here generally during emission, whatever the electron develop from this anode surface, this electron create a repulsion force with this anode space, because here from during emission what happens, from both the surface, both cathode as well as anode, due to this metallic breeze boiling, generally electron is start emitting. So, what happens, as the due to emission, electron is start emitting from this anode surface as well as cathode surface. So, whatever the electron is start emitting from this anode surface, this pull back to this anode surface itself. So, now whatever the electron coming out due to the ionized electron, that electron and this emitted electron generally creates some repulsion force over this anode space region. Due to this repulsion force of this emitted electron from anode surface and the ionized electron from this arc column, so they are generally create some sort of voltage drop in this anode space zone. So, generally in anode space, due to this repulsion force of emitted electron and ionized electron, there create a sharp drop of voltage in this region. Now, this last or fifth region of this arc structure is called anode spot. Anode spot zone. Generally, anode spot is the zone. This is the anode spot zone. anode spot zone where this electron absorbed. So, it is also a space or surface over the generally anode surface where the electron is absorbed. It's this region generally little bit bigger than this cathode spot region. So, this anode space also have a thickness within a range of 10 to the power minus 2 mm. So, due to this, that means what we observe, that means in case of a arc column, they are generally create 5 different zone. So, one is called cathode spot zone, another one is called cathode space zone, another one is called arc column zone, fourth one is anode space, and fifth one is called anode spot zone. So, we have observed that due to the why this different zone is there, these different zone generally create due to this emitted electron and ionization, that means ion and electron due to this that means this different zone is created due to this emission as and ionization of the arc column. So, after that actually detail about this thing is discussed in next slides, that means about this different zone, that means what is cathode spot zone, cathode space zone. I have already explained in details what is arc column zone. In case of cathode space and cathode anode space zone, there we observe sharp drop of voltage change, but in case of arc column zone, this voltage drop is not that much of high or sharp drop of voltage is not observed in case of arc column zone. Okay. So, this is the details about this different zone is describing in these slides. In next we will see due to this different zone or how the voltage drop is occur in a arc structure. So, here we will see what is the voltage drop region and what is the range of voltage generally drop what is the range of voltage we observe in different zone, that we will now discuss. So, here we will see that that means in between this column, in between this gap, that means cathode and anode, how much voltage drop is taken, total how much voltage drop is taken place, that I will explain here. And that voltage drop is actually is called welding voltage. That means whatever the voltage is supplied from the power source, that is not actually the welding voltage. The voltage drop which we observe in between this arc column, that is generally called welding voltage. Now, how this welding voltage is created and how it is distributed in arc column, that now I will explain here. So, generally here also I will show you, this is the electrode or cathode terminal and this is workpiece, or this is your cathode terminal, this is your job or anode terminal. Here generally the arc is developed. Now, in this arc how the voltage drop is look like, that I will explain here in details. So, this is generally the total arc length, this is generally total arc length L. Now, this axis, this horizontal axis or abscissa represent the voltage drop, or this is also generally called as potential drop zone. This represent the voltage or potential, and this axis represent the arc column, that means this axis represent the arc column, arc length. Now, generally how the voltage is taken place. So, here in cathode drop region, this cathode drop region is occur due to what? Due to cathode spot and cathode space, that what I have explained. This cathode drop region which has a thickness is around, cathode drop region which have a thickness around, just here I am just drawing cathode drop region, here generally a sharp drop of voltage is taken place. This thickness of this cathode drop zone, generally this is called cathode drop region, or you can say this is called generally cathode drop zone. So, here how much voltage drop is taken place? So, here we observe this mass of voltage drop. So, how much voltage we got here? We got a voltage drop of around this mass we observe. At sharp change of voltage drop is taken place in this zone. Then this is called, here also a gaseous space is there, negative terminal, generally here negative terminal, generally here positive space is there, that I have already explained in previous slide. At the end also in arc column, here this is my arc column, where voltage drop is not sharp. Okay. After that generally we get another voltage drop zone. This voltage drop zone or this voltage drop is occur from this voltage drop generally occur, because this axis I have already told you, this horizontal axis represent the voltage or potential, or so here generally this is called anode voltage drop, or you can say anode space voltage drop. This is called cathode space voltage drop, or you can say this is called anode space voltage drop, and or other way also we can say this is generally voltage drop in cathode drop zone. This is generally voltage drop cathode drop zone. This is voltage drop, this we can write in this way also, voltage drop in anode drop region, or we can say zone, whatever it is, anode drop region or anode drop zone. So, here whatever the voltage drop we observe, this voltage drop, that means from here to here, this voltage drop is called arc column voltage drop. This voltage drop is called arc column voltage drop. So, you see in case of arc column generally voltage drop is not that much of sharp, whereas in case of this cathode spot region and anode drop region, in case of cathode drop region, here generally we get sharp change of voltage drop. This length of anode drop region, is also within a range of, this is also within a range of 10 to the power 2 millimeter, whereas this cathode drop region, whatever distance cathode drop region, is also a range of around 10 to the power 2 millimeter. Now, here one things we can observe from here, voltage drop, if this means workpiece material and cathode material is remains same, then generally this voltage drop, generally this in anode drop region and cathode drop region generally will be remain constant. So, generally voltage drop is generally here, if this cathode material and anode material is constant, then this voltage drop generally will be depends on only arc length. Here whatever the arc length, if this arc length will be varying, then our voltage drop will change, but cathode drop and anode drop voltage drop generally will be remain constant if the material of cathode and anode will be same. So, what we observe, so in case of a welding arc, the welding voltage is how much? So, welding voltage here generally we are getting, so this much of voltage we are getting due to anode drop region, this much of voltage we are getting generally cathode drop region, and this is due to this voltage drop we are getting due to the arc column. So, this total voltage, that means this anode drop voltage, cathode drop voltage, that cathode drop voltage, anode drop voltage and arc column voltage, this total voltage is called welding voltage. So, how the voltage drop is taken place, that you understand, because I have explained what is the reason of this voltage drop, that also I have explained. Because this voltage drop in cathode drop region is occur because there is created resistance due to this positive ion concentration and emission of electron. Similarly, in anode drop region also, why this voltage drop is taken place, because in anode drop region generally there also creates some electron due to this emission process, and the electron attracted from the ionized gas, generally what happens, so they are generally create a repulsion. So, in this anode drop region, due to this repulsion there creates some resistance. So, as there creates some resistance, so there will be some voltage drop. So, how the voltage is created in welding regions, that you understand. And in arc column, why this voltage is coming, this arc column is voltage is coming, we know that resistance is proportional to, what we know, resistance is proportional to L, length of the arc, that we know. Then what we know, L by cross sectional area, L by A. So, what we observe, that resistance of arc length depends on length L. So, if the length of arc length change, then what happens, resistance will change. If the resistance will change, then we know that voltage is depends on generally directly proportional to R. Voltage is depends on R value, that we know. Voltage is proportional to this resistance R, that we know. So, if the resistance increase, then the voltage will increase definitely. So, in arc column, why the voltage drop is taken place, why the voltage change is taken place, because arc column have a length. So, there will be some voltage. So, how the total voltage is coming, that we understand. So, how the total welding voltage is generated in case of welding arc, that idea we get from this different voltage drop region, characteristics plot. From this voltage potential drop region of arc. So, different potential drop region of arc. From here we get the idea how the total welding voltage is generated in a arc. Generally, this voltage is responsible for generating the heat energy. How the, because that also I will explain in subsequent, that means how the arc power is generated. This also arc power is depends on this voltage, as well whatever the current is flowing on current also, that I will explain in subsequent slide. So, this is the voltage drop characteristics in a arc column, and how the voltage drop is taken place, that also we understand. So, from here we got the idea that this anode space and cathode space voltage drop zone or cathode voltage drop zone, generally voltage drop is remain constant if the material is constant, if that means cathode material and anode material is constant. But this so voltage generally change where? Voltage generally change in arc length. How it is changed, that I will explain in subsequent slide. So, before going to this voltage drop change in arc column, first of all here you should know actually what is the temperature distribution in a arc column as well as in a electrode, because that idea also here you should know, because then only you will get some fairly good idea how much temperature generally generated in due to a electric arc. Here just approximately I will just show you how the temperature distribution in case of a GTAW welding process. Let this is a tungsten electrode. So, this is a tungsten electrode. Now, generally how the temperature is varying over the range of one arc column as well as electrode, that we should know. So, generally this is the arc. Here I am just showing you that how the temperature is varying. In a arc column, the temperature is within a range of 11,000 degree Fahrenheit. Just approximately I am just telling, if the temperature in a arc column is within a 11,000 degree Fahrenheit, then tip of this, that means in cathode spot zone, the temperature is coming around 5300 degree Fahrenheit. it is generally little bit that means it is just outside this arc, the temperature is rise around, just approximately I am showing, so that you can get a feel, around 5000 degree centigrade. If it is just little bit away from this arc region, generally it has a temperature around 4000 degree Fahrenheit. So, this 11,000 degree, let us tungsten electrode, this tungsten have a melting point 6191 degree Fahrenheit, or in terms of centigrade, this is generally 3422 degree centigrade or 3422 degree centigrade. So, what idea we got, generally how the temperature changes from electrode tip to away from the electrode tip, that idea we got. It's generally this electrode does not go beyond its melting point in case of tungsten electrode, because if it's go beyond its melting point, then it will boil, melted, and what happens, this tungsten will be deposited with weld material. So, that will be a problem, no? That will be a defect of material. But here generally the temperature does not go beyond its melting point. If it is gone, then what happens, this electrode will be melted, that means electrode will be melted, then that will create some defect in weld zone. So, we should keep our temperature within this range. So, if a arc temperature is within a range of 11,000 degree centigrade, then how much degree, 11th degree Fahrenheit, then we get a temperature in case of cathode spot within a range of around 5300 degree Fahrenheit, which is around 1000 degree lesser than 1000 degree Fahrenheit lesser than the melting point of the tungsten electrode. So, here why this is required, because this is required because you can feel that okay, in a arc the temperature is 11,000 degree centigrade, then how much temperature is rise in case of a tungsten electrode, that also we should know, na? So, what happens, from here we get a very fairly good idea, though here the temperature is rising in a arc around 11,000 degree centigrade temperature, but in case of electrode tip its temperature is coming around half of that. Why? Because it's conduct the heat, that means in a electrode as it is colder than that arc region. So, what happens, this tungsten generally immediately conduct and dissipate the heat. So, it cannot, it generally not allow the temperature to rise beyond its melting point temperature. Definitely if the temperature will be higher in arc, then what happen, and if it is, so here we are not allowing, actually what we can say, here generally we are not allowing to rise the temperature beyond its melting point of the electrode. Why? Because if it is allowed to go beyond its melting point, then what happens, this electrode will melt and it will generally what happen, deposited over the surface, over the deposited with weld material. So, then that will create a problem. So, from here you get a fairly good idea, that means though the temperature is coming around 11,000 degree centigrade in a arc, but the temperature is coming around a tip of the electrode is around half of that, that is 5300 degree Fahrenheit temperature approximately I am telling, which is not goes beyond its melting point. So, which is not gone beyond its melting point of electrode. Okay. So, generally why? Because here generally heat immediately dissipated to this electrode. So, it is not allowed to rise the temperature. Okay. Now, we will go how to, what is arc power. So, before going to arc power, here one thing we should know, how the potential drop taken place due to change of current and voltage in a particular arc length, that we will see first. After that we will go for finding out the arc power. So, first of all we will see, so potential drop characteristics, here we will discuss for a particular arc length how the potential drop characteristics is look like. That actually already I have discussed a little bit, but here I will discuss in details. Generally potential drop characteristics in a particular arc length in a voltage current plot, in a voltage current plot for a particular arc length, how the voltage drop taken place if we change the current. That first of all we will see. The potential or voltage drop changes if the material or spacing between the electrode changes. However, a change in spacing and the current essentially change only the drop in the column, arc column. So, here one things we should keep it in mind, this voltage drop change if we change the current. That voltage drop is changed due to change of current in which region? In arc column only. This is not change in cathode drop region or anode drop region. This is change in which region? This is change in arc column region only. How it is changing, that I will explain now. Here what we can see, for a particular arc length, generally for a particular arc length, generally voltage drop characteristics is look like this. Initially with increase of current, for a particular, this is a particular arc length L1. This characteristic curve represent for a arc length L1. Generally this particular characteristic curve represent for a particular arc length L1 how the voltage drop change, that means voltage changes if we increase the current. So, what we observe from this curve, it is around 50 ampere current, it is around 50 ampere current, this voltage drop generally the voltage decreases. After that if we increase the current generally, then for a particular arc length the voltage increases. So, why it is occur, that we should know. Na? So, generally till a particular, that means till 50 ampere current, whatever the arc is generated, that arc shape look like cylindrical shape. That means that this arc, let this is your electrode, let this is arc. So, this arc generally look like cylindrical shape. So, what happens here, as this arc is look like cylindrical shape. So, if we increase the current inside this cylindrical region, the concentration of electron increase. So, concentration of electron increase means here generally resistance of the arc decrease. So, resistance of the arc decrease means voltage also will decrease, because what we know from Ohm's law, we know voltage is directly proportional to resistance. So, due to this concentration of more electron with increase of current, generally resistance decrease. So, resistance decrease means voltage also will be decreased. So, till 50 ampere current, this shape is generally remains almost cylindrical in nature. So, but above 50 ampere generally, if it goes above 50 ampere current, this arc, once it go beyond 50 ampere current, generally this arc is not able to get its shape like cylindrical shape. So, what happens here, this arc bulge out. So, what happens here, generally the arc bulge out, and what happens here, generally current path increase, this arc generally bulge out. So, in this case, so what happens here, the concentration of electron increase, as well as due to this bulge out of arc, generally this bulge out of arc, here current path, we can say current path length increases. So, as the current path length increases for a particular arc gap, generally here what, resistance increase, that we know, that with once resistance will increase, here again resistance increase means then voltage drop also will increase. So, that is why you see after 50 ampere current, this voltage drop is little bit increasing in nature. That means you see from this curve itself we can observe this, initially till 50 ampere current it is decreasing here, after that generally it is increasing, but this increasing also marginal. Why? This increasing of voltage is marginal because here generally two opposite phenomena taken place. Opposite phenomena means here two phenomena taken place. One is higher temperature we observe here, as well as a higher current carrying path we observe. Higher current carrying path means higher resistance we observe here. So, due to this two effect, that means high temperature and high resistance, here generally voltage drop is not that much very high. So, here generally voltage drop remain almost constant for a particular range of current. So, this is the generally voltage drop characteristics. Why it's happened, that we understand. This voltage drop till 50 ampere, around 50 ampere current. Here shape of the arc column is remains cylindrical in nature. Beyond this 50 ampere generally current, generally this arc generally start bulge out. So, what happens, one arc starts bulging, then what happens, its current carrying path length increase. So, current carrying path length increase means here generally, and its cross sectional area also increase, that means electron density also decrease. So, what happens due to this, here generally resistance increase. So, due to this increase of resistance after 50 ampere due to bulging out of that arc, generally what happens, this voltage drop little bit increase, but that increment is not very high, because what happens here generally, due to here generally high temperature is there. Due to this high temperature and high current carrying path, what happens here generally voltage drop cannot increase high. So, here voltage drop remain almost constant for a particular range of current. So, we got this idea how the voltage drop characteristic is taken place due to this change of arc length. Generally, characteristic for a particular arc length we got, how it's look like. Now, we will see if we increase the voltage drop, if we increase the arc length, then what will be the voltage drop, that also we will see. Here what we see, for different arc length, if the arc length increase, then the voltage drop increase, that we know. That means arc length increase means gap increase means resistance increase, because resistance is proportional to length. So, length increase, voltage is also proportional to R. So, what happens, if the length increase, arc gap increase, then generally what happens, voltage drop also increase in arc column. So, how it's look like, so for different voltage, for different arc length, how the voltage drop characteristics is look like, that I am showing. Let us, this is for L1 is equal to, let us 1 mm arc length, this is for 2 mm, let this is for 3 mm. So, what happens, arc length, this is for different arc length actually I am showing. So, for different arc length, how the voltage drop is generally taken place, that I am showing here. Just let us, what happens, if the arc length increase, then generally this voltage drop, voltage in the arc column increase. From this we can observe. Okay. Now, we will go for how to find out the arc power. That means, so arc power, what is arc power? Arc power means, we know that arc power is equal to voltage drop in arc column, whatever the total voltage drop, or welding, that is that arc column, whatever the total voltage drop is taken place, or the, that is called the welding voltage. So, arc power is equal to voltage drop in arc into supply of current from the power source. That means this is called welding current. So, power is equal to generally voltage into current, that we know, that generally power is equal to, arc power is equal to, this is in generally watt, that we know. If voltage is in volt and I is in current ampere, then this unit is generally power unit is watt, that we know. Now, so here before that, so here one things we should know, voltage drop characteristic for a particular arc length we can write, that means welding voltage we can write as A plus B into L. What is A? A represent whatever the voltage drop taken place in cathode drop region and anode drop region. So, this is not depends on arc length, but this BL is voltage drop in arc gap, that means gap between two electrode, gap between electrode and workpiece. So, as it depends on L, that is why it is represent in BL. So, it is a function of L, but this electrode, that means cathode drop and anode drop region, as it is not depends on L or L, it remain constant. If the material is constant, that's why we keep it as a constant value. So, voltage, that means total voltage drop in arc column we can represent as A plus BL. So, A is constant and BL is depends on length of the arc, that means gap between electrode and workpiece. By this equation, so we got voltage, welding voltage is equal to, we get as A plus BL. So, from previous discussion we got that idea. Now, how to find out this I? welding power. How to find out this arc I? Generally this I is find out from the working point. How the working point is find out? For a particular arc length, let us for a particular arc length L is equal to L1, we can easily get V1. That means V1 will be A plus B L1, because A and B is constant, it depends on only arc length. So, V1 we can easily calculate. Now, from this constant voltage or constant current power source characteristic curve, what we know? Always you keep it in mind, vertical line represent voltage and horizontal line represent current. So, there we observe that for a generally power source characteristic curves, how it look like? It look like this for a constant current power source characteristic. Now, what is working point? For a particular arc length, generally working point actually I have already explained. For a particular arc length where this arc length characteristic curves and this power source characteristic are crossing, that point is called working point. So, from first of all how to calculate the power? First of all, for a particular arc length we have to find out the V1. So, corresponding to this V1, let this is V1, let this is V1, corresponding to this V1 we have to find out I1 value. So, we can easily find out I1 value. Here V1 is a function of L, similarly I1 also will be a function of L. So, what happens? So, we can easily find out what is P1 value. P1 we can easily find out, P1 will be your generally P1 will be your V1 into I1. Okay. This way we can easily find out. Similarly, for another L is equal to L2 by using this equation 1, we can get V is equal to A plus BL2. Okay. So, whatever the V2 we got, so based on this V2, let this is my V2. So, based on this V2 from the power source characteristic curve we can get I2. So, we can get I2 from this power source characteristic I2. So, I2 is also a function of L2. So, we get P2 value. What will be the P2 will be V2 into I2. So, in this way generally for different arc length we can get different arc power. So, if we plot this arc length versus arc power, let this is my arc length and let this is my arc power P, then we will get a curve which is look like this. It does not mean that okay, if we increase the length then power will increase, not like that. We will observe that this characteristic curves is look like this. That means first it can increase, after certain arc length what happen? It can decrease. So, what happens for a particular arc length? Generally where we will get the maximum power, that arc length is called optimum arc length. So, here we will get a optimum arc length. So, how to find out the optimum arc length? That we get the idea. That means first of all by using this voltage drop equation we have to find the voltage. That voltage we have to generally put in power source characteristic curve. From this power source characteristic curve we have to find out the I value. So, multiplication of V and I will give the power. So, what happened based on this power? If we just plot power versus arc length, then there we observe that okay, for a particular arc length we will get maximum power. That maximum power generally corresponding to which arc length we are getting, that arc length is called optimum arc length. So, generally we should use optimum arc length so that we can get a optimum power over there. This is one way. So, by finding out the power for different arc length and plot it in a curve, from there we can find out the arc length. Another way also we can do, like here generally here power is a function of V into I, where V is a function of L as well as I is a function of L. So, what happens if we just derivative this with respect to L and make it equal to 0, from here also we can get L optimum value. This way also we can. So, this is the step how to find out the optimum arc power, so that we can get optimum arc length, so that we can use this optimum arc length during our actual welding process. So, we understand how to find out the optimum arc length, and this is generally the procedure. for finding out the optimum arc length. Now, we will solve 1-2 problem on this optimum arc length, then our idea will be very clear. So, here one problem, just first of all I will solve. After that, generally 1-2 problem if I will solve, then it will be very clear. So, one problem, this is a problem 1 for finding out the optimum power and optimum arc length. The problem is look like here. The voltage arc length characteristics of a direct current, here is a DC current, arc is given by V is equal to 20 plus. So, here V is equal to given as A plus BL. So, A is 20, here B is 40 and L is generally length of the arc. Okay. See this here, what is the thing given? L is in centimeter, this is given. Okay. L is in centimeter, here it is given. Now, the power source characteristics is approximated by a straight line. This is a very interesting term, here it is used. Generally, power source characteristic, what we observe, generally in case of constant current, it is curve in nature. But here what it consider, the power source characteristic curve means there is a current and voltage, that means coordinate is voltage and abscissa is current. So, it is a straight line characteristic. Instead of curve characteristics, here what it is considered, here instead of curve characteristic, here it is considered as a straight line characteristics. Here we know this thing, this is called generally open circuit voltage VO, we are representing this in VO, open circuit voltage. This open circuit voltage is given as 80 volt and this is called generally short circuit current IS, which is generally given as, this VO is given as here, VO is given as 80 volt and IS is given as, short circuit current is given as 1000 ampere, 1000 ampere. Okay. This is given. So, by this information I have to find out what is the optimum arc length and what is the optimum power. That means, here what are the things I have to find, what is the optimum arc length and what is the P optimum. These two things I have to find out. How to find out this thing? So, we know this, we have given this voltage drop equation, which is a function of L. Now, we have to find out, we know that power is what? Power is generally is equal to V into I. So, first of all, V is a function of L we got. Now, I also we have to find out, which will be a function of L. How we can find out? For that, for a particular voltage, by using this power source characteristics we can get I. Let this I am representing in terms of, let this is your A point, this is your B point, this is C point, this is D point and this is E point. This point is E point. Now, from similarity of two triangle, so what happens here? From the similarity of two triangle, what is this two triangle? Triangle A, B, C and triangle A, D, E. What we got? What we can write from the similarity of two triangle? We can write as AB by AD, because this two triangle is similar to each other, is equal to, we can write as BC by DE, correct? So, generally here everything AB is generally, this AB is equal to what we can write? V0 minus V, correct? Because from here to here, this is V and total is V0, open circuit voltage is V0. So, AB we can write as V minus V0 and AD we can write as AD is equal to, AD generally is your open circuit voltage, AD, because this AD means this is A, this is D. Okay. So, this I am just writing here, then it will be more clear. So, generally, so AD equal to this. So, what is BC? BC means, from here we can easily see, BC means I, and what is DE? DE is your IS. So, from here generally we can easily get what is I value. So, I is equal to we can get as, so from here first of all we will see what is V. Directly I am putting this thing. So, V we can write as V is equal to we can write as V0 minus V0 into I by Is, correct. From this equation we can get. So, this equal to V0 is equal to given as 80 minus this is also 80 into I by 1000. So, from this power source characteristics also we get this V, and from this arc length characteristics also we get the V. So, now this is let us equation 1 and let this is equation 2. So, from this equation 1 and 2, so 1 and if we equate this equation 1 and equation 2, what we will get? We will get I in terms of L. How it is that I am showing. So, what we can write? So, equating equation 1 equal to equation 2, what we get? 20 plus 40 L will be is equal to your 80 minus 80 into I by 1000. Okay. So, what we got? So, from here I we can get as, so I will be your just 60 minus 40 L into 60 minus 40 into 1000 divided by 80, correct. So, I we got as like this. So, I we got as like this. So, this 80 cancel, this will be cancelled out. So, this we can write as 60 minus 40 L into, what will be the, if you just cut it to 25, okay, 20 to 25. Okay. So, I we got as like this. So, what will be the power now? So, here we know, so we got this, let this equation 3. So, equation number 3 we got. Now, what will be the power? We know power is equal to generally. So, here what we got? That means this I is a function of L as well as this B is also a function of L. These two things we got, correct. So, what will be the power here now? Power will be generally V into I. Power will be what? V into I. So, this power, so arc power what we can write? V is equal to generally 20 plus 40 L, and current is how much? 60 minus 40 L into 25 by 2. Now, for optimum arc length, what we have to do? We have to do del P by del L, and we have to make it equal to 0. So, once we do these things, what we will get? We will get del P by del L of this equation, of that equation. What we will get? We will get what? You see, we can easily see 40 into 60 minus 40 L 25 by 2 minus 40 into 20 plus 40 L into 25 by 2, correct. And if we make it equal to 0, if we just, so I am just erasing this portion, okay, and put the things there. So, now, so del P by del X we got. How we got this thing del P by del X? That means first of all derivative of this portion, this portion, and rest of the part will be there, and next case derivation of this portion and rest of the part will be there. Okay. So, it will be like this. So, if we make del P by del L is equal to 0, then we will get L is equal to how much? 0.5. You just do the calculation, you will get the thing from here itself. Here L is in the terms of given here L unit is centimeter. So, here L will be centimeter. So, we got this L value. This is generally what? This is generally L optimum, we can say. This is L optimum value. So, what will be the power optimum? So, optimum power will be your corresponding to this L. If we just multiply this thing, that means V into I corresponding to this L is equal to 0.5 centimeter. If we will do, then we will get the optimum power. So, optimum power will be how much? V into I, V means 20 plus 40 into L means your 0.5, and I optimum, or what will be the optimum current? Optimum current will be from equation 3, 60 minus 40 into 0.5 into what? Into 25 by 2, 25 by 2, which is generally 20 kilovolt ampere, or you can say this is equal to 20 kilowatt. So, this is one problem which shows how to calculate the optimum arc length and optimum power of a particular welding operation, or of a particular welding operation that it is showing. Next class actually also I will solve 1-2 problem on these types of arc power characteristics, and will show generally how to find out the optimum power, as well as how to let's optimum power is given to us, then how to find out this open circuit voltage, how to find out the open circuit voltage, how to find out the short circuit current. So, that we will see, and if we have these types of idea with us, if we have these types of idea, that's how to find out the optimum arc length, then also we can characterize, or we can design a welding power source as per our requirement. So, next class I will discuss in details about arc power calculation and arc power related problem. After that we will go for other topics on physics of welding.